2.
The Mafra is still arriving. Maybe you can start, but slowly.
Okay.
Take the first 2 minutes to follow.
Okay. Okay, so I should start by saying that I forgot to say a few things in the last lecture, and one of them is to thank the organizers for the invitation. So thank you. I forgot. The other thing that I forgot to make it explicit was that I said that the pure spinor is a spinor, but in order to know that something is a spinor, you need to know the Lorentz generator that under which you can say that the spinor is transforming under the spinor representation for the Lorentz group. And in this case, the Lorentz generator is big. Okay. Is this one, and it satisfies the following OP. And now it's and then there are some indices here, P, N, M, Q, and then the antisymmetric Q, N, MP, and here it's M, Q, P, N. And this number here is called the level. So it's level, this algebra here has level -3. The other thing that I forgot to emphasize was that the pure spinor constraint is very strong, and so the pure spinor constraint was this one, right? But you can also show that because lambda is a pure spinor, you also the 3 form also vanishes. Why? Because I mentioned that the 3 form is antisymmetric in the spinor indices, and the pure spinor is a bosonic variable, so it's symmetric in the spinor indices. So it's, once you contract, it's 0. So and from these you get all sorts of vanishing combinations, and anything with 3 lambda gammas in between the pure spinors is 0. So, and in fact, the only non-vanishing bilinear is the 5 form, Mn, P, Q, R, lambda. That is different from 0. That's the only bilinear that survives the pure spinor constraint. And but you can also show other vanishing conditions simply because lambda is a pure spinor and using some gamma matrix identities. For example, if lambda is a pure spinor, then you get that this is M, so it's contracted. This is 0 no matter what you contract in the in the spinor indices. So this is completely general, and to show this, you just need to use the gamma matrix identity that I wrote down yesterday. That you symmetrize alpha, beta, gamma. That's 0, and then from here you will get that this is equal to minus alpha, and then another term which is minus lambda gamma m lambda, then gamma m alpha beta, but this is 0 because of the pure spinor constraint. So you get that this is minus the same thing, so it's identically 0. And these kind of identities here, they are essential to simplify amplitude computations, and because they are very restrictive, and you simply cannot get too many combinations out of the superfoods that I will mention before, simply because almost everything vanishes. Okay, so yeah, so that is what I forgot to do, and now I'm going to move on. By the end of the last lecture, I said that we wanted to find two vertex operators that we are going to use to compute the amplitudes, and I mentioned them in the context of the tree-level amplitudes, but they also appear at loop level. They are the same vertices. So and the amplitudes that we are going to compute, they are for the gluon multiplate. So the gluon supermultiplate of Superang Mills in 10 dimensions. So in order to present you the solution of these vertices, I need to talk about Superang Mills in 10 dimensions. Yeah, so anyone has questions from yesterday? Okay, so yeah, so
I have a basic question. Why did we start with some wrong action as a way of motivating?
Oh, okay. Yeah, it was not a wrong action actually. It's the thing that I said about lying was a bit. Oh, yeah, okay.
I did not understand very well in the end what was the motivation. So we start with some Siegel proposal that, as you explained, doesn't make sense wrong.
Yeah, but
Why is it?
Well, Siegel. Well, it was in 1985 actually instead of 86, but Siegel wanted to construct some action for the superstring, and that was his proposal, but it didn't work. But it was there. The paper was published and everybody could read it, and then Berkowitz read the paper and then found the missing pieces to make it work. So it was a wrong thing that could be fixed to find something useful. And by the way, I didn't really lie yesterday. Everything that I said was correct, but was slightly more subtle. So recall that 10-dimensional Superang Mills has the following action. It's it's minus 1 over 4 x squared so that's the action for 10-dimensional superrank mules, where F is the field strength and chi describes the gluino. So so F Mn. I have the impression that I should not be spelling these out, but just for completeness. F A B C and then B N A C N, and the covariant derivative, well, it's something of this form. It's plus AM. Well, with the gauge indices appropriately there, and from now on I'm going to drop the gauge indices, and the action is very simple. The spectrum is very simple, just a gluon and a gluino, and the equations of motion that follow from the action are the Dirac equation and the standard one. And contracted with the gamma matrix. I guess people over there cannot read this one, but it's it's chi gamma n. Okay, so these are the equations of motion, and you can also show that this is supersymmetric, but we are not going to need the supersymmetry variations. What I wanted to motivate here is that these two equations here can also be described in terms of superfields, and the superfields will be important to describe in the context of the superstring. So that's what I'm going to show, how you can describe these equations from superspace. So 10-dimensional superspace contains the x and theta variables, and the superfields that we are going to use to describe them, to describe superrank mules is this one, and then that one also x and theta here, but just to save some time, I'm not going to write the x and thetas. But so we have 4 types of superfields that will be used to describe superrank mules. And to do that, you define covariant derivatives, like using this, the superfield there, right? And this is the covariant derivative that I wrote down yesterday. Right, and the other covariant derivative is del m minus am, where it's also the superfield. And you can also define field strength from these covariant derivatives. And
Sorry, what's the end?
what?
The end of the M.
Okay, thank you. It's the momentum or the derivative. And okay, thank you. I forgot. So you define the field strength like this. You also define another field strength with spinor indices like minus gamma m of beta. So far we have just definitions, and the appearance of W is through this definition is it's minus del M minus or plus. Okay, so it's plus. Okay, so let me just follow my notes here and the claim. Okay, so the definition is stopped, and the claim is that the equations of motion will follow from setting these superfields to 0. So you set this guy to 0. So and doing this, you will get four types of equations. The first one is that one, and I will just write it again here because we're going to use later. And the second one, this is a definition, but it's also already a solution. But so the second one is that and then the third one, it's I'm going to run out of space. And the fourth one is the covariant derivative acting on Fmn, and that gives you the anti-symmetrized combination of okay, so it's slightly unreadable, but that's what it is. So you get these four types of equations just by setting this one to 0. And how you can convince yourself about this? And the way to see this is by using Bianchi identities and using the definitions of the field strengths that that I wrote down before. So let's just check this one there, number 2, and this equation will follow from the Bianchi identity with 3 covariant derivatives plus cyclic alpha beta gamma. that is identically 0, right? It's, you just expand everything and collect terms and you get 0. And so let's just check that this makes sense. So this equation here tells us that this guy is this one, right? So now the so now you will get gamma p alpha beta, and then del p del gamma plus cyclic. But this one here with p and gamma is this one, right? So let's just write what it is. It's minus gamma p alpha beta, and then gamma p. Let's see. It's gamma delta w delta plus cyclic in alpha beta gamma. So you see cyclic alpha beta gamma, and that is 0 because of the identity that I wrote down yesterday, and this one here. So that is why I said that this definition is definition, but also already a solution for what we wanted to show. And the non-trivial identities that you get are the 3 and the 4. And to show the third equation, you need to use the Bianchi identity with 2 spinor indices and one vector index, and plus cyclic alpha beta and m, right? But I will not do this explicit here, but you can just use the definitions and plug everything here, and then you find that equation after some gamma matrix gymnastics. And similarly, you can show that the fourth equation follows from the Bianchi identity with 1 spinor index and 2 vector indices. Okay, so but now we have these equations here, and they don't look anything like these ones that I wanted to get in the beginning. So what can you do to make these equations more familiar? So you start with equation 3, and you write it like this. Of beta and then fmn, and now you multiply both sides by delta gamma and symmetrize in alpha and gamma. So that's what you get. But this equation here, we know what it is, right? It's gamma p alpha gamma delta p. Okay. And in this side here, you use this equation here to get the derivative gamma matrix and w. So you will get something here. I will not write it down explicitly here, but so the left hand side now you can contract the spinor indices here. So you contract this one, so this equation here becomes this side of the equation becomes this one, and if you follow the gamma matrix manipulations that you need to do, you will discover that the right hand side becomes proportional to the left hand side. So in the end, what you get is that what you conclude is that this guy here is 0. So that's the Dirac equation here, but now in superspace where the gluino became a superfield. And similarly, now you know that this equation is true, and then you can also manipulate it a bit further. And yeah, okay, I just mentioned that say you multiply this equation by something like this, and then do a lot of manipulations, and you will obtain the equation that we wanted. But now these guys are the superfields alpha. I feel a bit bad about omitting the steps, but the steps are a bit they're straightforward. But so okay, yeah. So this guy here is the superfield now. So we obtained what we wanted. We now have a description in superspace, 10 dimensions of the equations of motion. But these guys are superfields now. So they have theta expansions. So well, the original reasoning was something along the lines that, well, this is a field strength, and if you analyze the dimensions of the mass dimensions of these guys here, you get, say, 1. Yeah, I think it's 1, and just from knowing what you want to get, you know that you don't have any field strength of dimension 1 there. So the natural thing to do was to set this guy to 0, and then doing that it worked. So it should be. No, not really. Yeah. So yeah, as far as I know, there is no action that in superspace that these equations here follow from the standard procedure. I think that is related to the problem of finding an off-shell. Okay, nah, forget about it. But I don't know about the action that generates these equations, but we have the equations, so let's live with them. So, but so these are the 4 equations that are equivalent to the nonlinear equations of superrank mules, and so they are really, well, they are nonlinear, right? It's there are quadratic terms there, and even though people have recently found a solution for these nonlinear equations, what we are going to need in the following are just the linearized versions of these equations. So I will just write them down here. And these equations will be used very frequently until the last lecture.
Sorry, could you mention where the physical component is embedded in the superfield?
What?
So where is those chi and?
Okay, yeah. So, but I'm going to do that in 3 minutes.
Okay.
So the second equation becomes the momentum of the particle, and in the third equation and these numberings, the numbers of these equations here will be important, because later on I will just mention that, okay, using equation 2 you get something. So these will be the numbers. Okay, so I think I said that my convention for antisymmetrization has 1 over n factorial, so it's but okay. So these are the linearized versions, equations of motion. So linearized equations of motion. And now I said, okay, so they are superfields, and in particular they have the theta expansions, and so that's going to address his question. And we want to find, we want the theta expansions. So, I forgot to say something here that is very important. The description of gauge invariance in this language here. If you do a gauge transformation on the superfields, well, on the fields, the gauge transformations are encoded in a scalar superfield like that, and this is how the superfields vary, and the field strengths F and W are invariant. And I should say that this W is also called the field strength for the gluino. Okay, so these are the gauge variations in superspace. And we now want to compute the theta expansions. And in particular, let's have a notation for what we want to do. We want to compute the components of a particular superfield, say particular. I'm not going to use a letter that is with n n theta variables. So that it will be something like alpha 1 to alpha n and theta alpha 1 theta alpha n. So that's going to be the definition of the bracket there. It's something with that number of theta variables. And of course the limit is that you don't get anything more than 16 thetas. Okay, so right after this description right after this description was published, some mathematicians were interested in checking that everything could be proven, and then they came out they came up with a prescription to compute the theta expansions. So they said, okay, let's fix a gauge like this. Some people call this Vezo-Minu gauge or something, but if you contract theta with a alpha, you should get 0. So that's the gauge that they proposed, and from this condition you can get the theta expansion. So let's see how this works. Okay, so if this is true, then it's also true that the derivative of that is 0. And if you compute the derivative there, you will get alpha beta, and now you anti-commute. So that's what you get. And now you use equation of motion number 1 here to write this as minus del alpha a beta plus gamma m, right? And so now you get that 0 is equal to plus theta contracted to covariant derivative of a beta minus gamma m. Minus gamma m theta beta alpha m. So what is this guy here? This guy can be obtained. You can look what you get from here. So you contract. So from this equation, you can see that if you contract this guy, you will get just the first one here, because the gamma matrix here is symmetric and the thetas are fermionic. So you get this one, and so you get that this is just the standard thing like that, and now we want to compute the component with n thetas, and for that you just need say a lemma that whatever this guy is, once you evaluate this guy, you will get n times the same thing. So let's use it here, and doing this here, you will get 1 plus. Okay, so now let's say we want to compute the nth component here, and now we have a theta here, so this should be n minus 1. So you get 1 plus n. Okay, so let me. alpha beta n, and then that is equal to so you can relate the component with n minus 1 thetas in the vector potential with the nth component of the spinor potential. So that is one equation that you can get from here. But you can also get other equations. You can also get two other equations. So let's see the other one. Let's simply multiply the equation, this equation here, equation number 2 by theta alpha. So you will get rid of this term, and you will get a recursion for this that will relate AM with W. So I will just write down the solution that will allow you to compute these things yourself. Okay, no. Oh my God. Okay, let me not write down the equations, but the end result will be that, well, you will have two more equations like this that you can find in the notes, and the punchline will be that you can find all the components by just starting with the zeroth component of the vector, and the zeroth component of the field strength, like this, and the zeroth component of the field strength, like that. I should have used lowercase f for the components, but so if you start with this, so that is where you see the gluino and the gluon. If you start from this set of data, then you find all the 16 data components of the superfield. And very quickly, it's just a recursion. It's okay. So okay, let me just write down the end result for this one, because it will be important for what we are going to what I left as something to do today from yesterday. Okay, so and then plus other terms. So the component with 1 theta in W has the field strength like this. So we are going to use this equation in a moment. But now we know, well, everything about these superfields, and we can now write down the solution for the vertex operators that we wanted. And and the solution will be V is lambda alpha A alpha, and U, oh, this has, okay, let me. Okay, so this guy has conformal weight 0, and this guy has conformal weight 1, which were one of the conditions that we wanted to satisfy. And by the way, this part here was already in the paper by Siegel. He already arrived very close to the answer. He said, okay, based on some supersymmetry arguments, that is what the vertex should look like. But in addition, we wanted the vertices to satisfy that Q of V is 0 and Q of U is del V. So let's prove equation number 1, this one here. So oh no. Oh, man. Okay, so let's check what his Q of V is. The BRST charge was defined like this, where d alpha is the Green-Schwarz constraint. And when it acts on a superfield that depends only on x and theta, the action of the BRST charge is just the pure spinor contracted with the covariant derivative on the superfield. And the covariant derivative is over there. So let's do this for V. If you do that for V, you get lambda alpha, lambda beta, del alpha, del beta, where I used the solution for V. So the pure spinor is bosonic, so this guy is symmetric in alpha beta, so I project into the symmetric part of this one. But now if I use the equation of motion 1 over there, this one becomes lambda gamma m lambda am, and this guy is 0 because it's the pure spinor constraint. So V is BRST closed as we wanted, and that is another appearance of the pure spinor constraint. And so okay, yeah. And to show that Q of U is del V, that's an exercise, because I'm running out of. Yes. Yeah, that's the linearized version. I said that after arriving at that point, I was going to use the linearized versions because, well, this is perturbation theory after all, right? So So that's true. And by the way, Paul Hall had already observed this in 1991, that pure spinor simplified the description of Superfoods meals in 10 dimensions. So and now another thing that we can do is to check what happens under the gauge variations. So under gauge variations, so the gauge variation acts on V as Q of something, so it's BRST trivial or exact, and the gauge variation on the U vertex is del theta, this guy, plus, and if you use the chain rule, you will find that this is nothing more than the derivative of omega. So what you conclude is that the gauge variation of the U vertex when it's integrated is 0. So the gauge variation of V is BRST trivial, and U is the gauge variation of the integrated vertex is, well, it's infinite. Okay. So now I want to come back to the point that I left from the last lecture, because well, Siegel already knew this part of the vertex, and now we can check what it is in terms of the components of the superfoods. And if you plug in the theta expansions for these guys, there will be a cancellation between these and that one, and well, in the end you will get something like this. You will get del xm, and now okay, the polarization for the glue, so that, and then from this term you will get 1/2 of the charge that so this is the Lorentz generator that I wrote yesterday for the p and theta variables, and it looks like this. That is the generator, and I mentioned that the level of this algebra is +4, right? And but now you can look at this term here, and you can compare with what you already know from the RNS formulation, for example. And in the RNS, you will have a vertex that is like this, and in some ghost picture, it will look like this, but these are the Lorentz generator for these guys in the RNS formulation. But there is a essential difference, that the level of this algebra there is +1, and here you get the same structure but with level +4. So that was one of the observations that Perkovitz had when he proposed the pure spinor formulation, because now he said, okay, now I need to add this term here, because then this term gets corrected to this one if you use the first data expansion from the F superfield, and this guy has level -3. So in the end you get something with level +1. So you can start to hope that whatever you get here will be equivalent to the RNS. So that fills out the point that I raised yesterday. So I have like 20 minutes left, right? Or that's 56. Okay. Okay. So now we have almost all the elements that will be essential. Well, we almost completed the description of the formalism. So let's just get the last step done, and then we will be able to compute amplitudes. I mentioned yesterday that the prescription to compute the endpoint amplitude at tree level would be something like this. It's a path integral over the vertices, and these three guys here are fixed at position 0, 1, and infinity, and by now you are familiar with these three numbers here from David's lecture, because they are used to fix the residual conformal symmetry of the disk, for example here, for the open string. So we want to compute the open string, and so it will be the Superfoods multiplet. So now we know about these vertices, and the prescription to compute this correlator will be to use the OPEs of the variables that appear in the vertices. So in particular, well, you remove the conformal weight 1 variables through their OPEs, and I wrote down all the OPEs that are needed in this computation yesterday. So for example, the alpha with the beta is something like alpha. And then doing this, you can get rid of all conformal weight 1 variables. But you see from you can see from this OPE here that I didn't write. It's that just using the OPEs, you cannot get rid of the lambda variables of the pure spinors, and there are 3 of them here. And the fancy way to say this is that you cannot eliminate the 0 modes of the pure spinor. The pure spinor has a conformal weight 0. So no matter what you do here with the OPEs, in the end you will get an expression with 3 pure spinors, and some superfield, some theta variables that will come from the expansions of the superfields, right? Because we have all superfields inside there. So you will get a function of superfields or of thetas, and then the polarizations of the superfields and all that, right? So you get something like this. So you need a prescription to eliminate, to do this last path integral, and that is the last step in the formulation. So the prescription was found by Berkowitz, and he said that when you do this computation, you should look at the component. Let me write it here. And he said that, well, let's fix this integration by setting that this combination here, the path integral of this guy is 1, where and this combination here, I'm going to write define a shorthand notation for this one. It's lambda 3 theta 5. So whatever you get here, you will just need to look at the components that are proportional to this one, and then the result of the amplitude will be whatever is in front of that. So, but what is interesting about this measure here okay, so let me say a few words about it. So the first thing that you should notice about the measure is that it's in the cohomology of the BRST charge. And by the way, there was no escape from this one, because the only Lorentz scalar that you can construct from three pure spinors and a bunch of thetas is if you pick only 5 of the thetas. So okay, let me just so lambda 3 theta 5 is in the cohomology of Q, and you can easily convince yourself that lambda 3 theta 5 is closed, right? Because when Q hits here, lambda gamma m theta. So when Q hits on these 3 factors, you just get the pure spinor constraint, and that's 0. When Q hits here, you will get something like lambda gamma mn p theta. But now you can write these as lambda gamma m and p theta plus or minus delta m n lambda p theta, and you symmetrize np. But now the first term will be 0 because of this one, and the other 2 terms will also be 0 because of that, because they are contracted with things like this. So it's in the it's closed, and lambda 3 theta 5 is not the BRST variation of something else, because this something else would have to be something with 2 lambdas and 6 thetas, and there is no scalar that you can construct from these variables. And if you can, for example, use a program called Lee to check this. So lambda 2 is this representation of SO10, and then you pick the anti-symmetrized combination of 6 thetas, and theta is in this combination here. So you anti-symmetrize 6 of these, and then you check the tensor product between them, and you find no scalar there. So it's in the cohomology. And 9 minutes. Okay, I just want to mention for example, suppose you don't believe me or you don't believe Lee, that there is no scalar. And then you say, okay, I found a scalar, and let me write the scalar for you. Oops. Mn A PQ B and theta R AB. Right? This looks like a scalar. Everything is contracted, and there are 2 pure spinors and 6 thetas. So what's going on? But the thing to notice is that this guy here is symmetric under the exchange of A and B. A is here, B is there, and then Mn PQ. And if you swap Mn PQ here, it's symmetric, and this guy is anti-symmetric in AB, so you get 0. So Lee is correct. Okay, so let me just finish this talk by summarizing, by stating what is so special about this language to describe amplitudes. Because I guess that up to now has been a lot of formalism, and it should be important to have the perspective of what we want to do. So there is a strong interplay between among the facts that I stated here. First one is the cohomology properties of lambda 3 theta 5, right? Because that is the kind of stuff that you get in the end of your computation, and we just checked that it's in the cohomology of the pure spinor BRC charge. So it's in the cohomology of Q. And the second point is that Q by itself is very simple. When it acts on superfoods, that's it. Lambda and the covariant derivative, right? And we just went through all these manipulations with the equations of motion that involve this with d alpha. So this guy here is simple. And the equations of motion are also simple, right? It's just a few terms. And they involve the covariant derivative here in a very simple way. right? You just get the. So the equations of motion are simple. Remember that we are in 10 dimensions, and in 10 dimensions everything is simple. The equations of motion are simple, and they are very deeply connected to the BRST charge. They are very closely related. And okay, and what else? Okay, and we have the pure spinner. There is a pure spinner. There will be 3 pure spinners actually. There are 3 pure spinners lying around. And I just started this lecture by mentioning how restrictive the space of pure spinner is, because you get zeros everywhere, simply because you don't have too many. There is not too many freedom to write things that don't vanish. So there are 3 pure spinners, and that constrains your answers a lot. It's very. So this structure here. So these 4 statements, when taken together, they are very, very powerful to analyze the amplitudes. And these guys, if you simply play around with these facts by what you get with the amplitudes, you will see many surprising relations, and you will find that things are nice in the end. So these 4 guys here can be stated as pure spin or superspace, as being a concept that is powerful, and pure spin or superspace is a space is the standard 10-dimensional superspace with lambdas and thetas, and now the pure spinner, such that you have the measure with 5 thetas. So this guy here will be the main actor that will allow the endpoint amplitude to be written down in a very, very simple manner for the string amplitude and for the field theory limit. And I think, well, 2 minutes. What can I do in 2 minutes? There is something crucial, I guess. So let's just check that this prescription here is gauge invariant. It will take just a few lines. And it will. So let's compute the gauge variation of this guy. So the gauge variation, suppose with respect to particle 1. So it's that one. So we just observed that the gauge variation is BRST exact. So it's something like this, Q of that, and then the rest. But now I stated that the measure that you get is in the cohomology. So you can integrate the BRST charge by parts. And when you do that, you get that this is Q of everything minus the correlator of omega 1, and then Q acting on the rest of the amplitude. But this is 0 because of the cohomology. The BRST, the the pure spinor bracket of a BRST exact quantity is 0, simply because the measure is in the cohomology. And this guy is 0 because everything else here is BRST closed. These guys are BRST closed, and these guys are also BRST closed once you integrate over the surface. So the gauge variation of the amplitude is 0, and we already used some cohomology manipulation there. So yeah, that's I just want to mention one more thing, very briefly, that exemplifies what I mentioned with these 4 points there. And I hope that this will create some motivation. So that's what I'm. So, for example, the two-loop amplitude for 4 points was computed in 2005, and that in the end you get a kinematic factor that looks like this: NPQR lambda, then that is the two-loop kinematic factor for 4 points. You do this computation, and that's what you get. 2 loops. Okay, I drew there the closed string and the closed string, and then it says the square. And the one-loop amplitude was computed in 2004. And this was the result that was obtained. So these guys are all supersymmetric. Everything is in here. The gluons, gluinos, or gravitons and gravitini, and all the Hamon partners, everything. And okay, so these were the two results at 2 loops and 1 loop. The amplitude had this kinematic factor and multiply some integral, right? And you could square this to get the closed string. And you look at these two expressions, and then you say, whoa, okay, they are compact, but yeah, okay, they look different from one another. But if you use these manipulations that I mentioned before, you will get that you will find a superspace proof that K2 is actually, let me write down, K1, K2. So they are very simply related just by using pure spinor superspace manipulations. You can prove at the superspace level that they are proportional by a Mandelstam invariant. And once you do this, you're showing the equivalence between the 2-loop amplitude and 1-loop amplitude for everything. Hamon, Neves-Schwarz, everything. Everything is in there. So these kind of manipulations in pure spinor superspace, they are very useful for analyzing amplitudes in a supersymmetric way. So that's it.
How to prove that the invariance of pitch is the
that doesn't really matter. You can choose you can choose any any label for these guys. It's totally invariant, and the way to prove this is you need to use something like this, that Q of U is del V. So and then and then you integrate these, so you get V here, and this side. Well, and then for this guy, and for this guy you integrate the BRC charge by parts. So you will produce V's somewhere else. So in this sense, you can swap. You can change the notion that V1 was unintegrated to being integrated, and something like that. It's independent. That's right, and that's related to the proof of cyclic invariance of the amplitude. But so this might have looked a bit heavy, but now I think we are at the top of the mountain, and then we will have a good overview of what will happen with the amplitudes, and from now on I think it's downhill. So
I heard some
Sorry? Yeah, for me, we can get started. I got the cake in that.
Okay, very good.
It's working, but if I push play, it doesn't work. So. Okay, so this is where we were. I showed you the data, and I explained how these data points are obtained, more or less, not in too much detail, but in some detail. So if there's any questions, I guess at this point maybe let me know. If not, then now the question is, how would we make predictions for this data? And there's different ways of calculating now in this theory. The standard way is to just take the theory that we had. So we had our theory, which was really just the Nambu-Goto action in static gauge. And then so squared, and then plus 1/4 the other one. Plus dot dot dot, and then what you want to do, so these are objects that live on a circle, so the standard thing to do is to just compactify the theory on a circle, make one of the directions compact, and then work out the a spectrum of excitations. So if you look at it for the ground state, diagrammatically, if you compute the energy, you get contributions. Well, there's the classical linear piece, which just gives you this contribution, so I call it 1. And then there's a number of additional contributions. Diagrammatically, the first correction is just a one loop piece, and you just get d minus 2 pi over 6, and then ls over r squared. And this should actually also look familiar from what we've seen in many discussions, because here what's supposed to appear at leading order at 1 over r, this is the central charge of the IR CFT, and you see that you just get a central charge of d minus 2 because we have d minus 2 free bosons. So this is good. This is the one loop piece, and then you can keep going and you find d minus 2 squared, and then I think there's pi squared, but I can look it up. Yeah, let me look up the exact formula. So there's the next one. So this is comes from diagrams of this form, and again, I mean, just using these quartic vertices, these two quartic vertices, you compute these diagrams, you get this contribution, and then there's also a piece d minus 2 for at 3 loops, cubed, pi cubed over 432 ls over r to the 6 plus dot dot dot. And the nice thing was that we said there were no extrinsic curvature pieces, so they would have contributed at this order. So up to this order, it's actually completely universal. The only parameter you have in your theory is the string tension or the string scale, and then up all the dots here are non-universal. And so this is a prediction, has one free parameter, the string tension, and you can then try to compare it. So what you do is you fit that one parameter and look at the rest. And what I'm showing, what I'll always show in my plots, is not the energy itself, but it's the energy minus the classical piece. The classical piece is relatively boring. If you show it, then the plot, I mean, it just is so stretched. I mean, the scale, you don't see any error bars or anything, but you're really just seeing the classical linear piece. So what you're seeing is not that interesting. So let's take out the linear piece, and then you see some structure. And the expansion that I'm showing here is the green dashed lines, and then I'll discuss what this line is in a second. But so this is the most straightforward way to do these calculations, and this works well for the ground state. And so what you can do is do it for excited states, and you again compute diagrams. You can again go up to this order, and I won't write down the expressions, but I mean this is the same structure, again an expansion in LS over R squared. And so here what I'm showing you, so this is the ground state that we just looked at, and then this state here is a state we also saw before. This is the state with a single left moving or a single right moving excitation on the string, and the expansion, this derivative expansion, gives you something that works well out here for R over Ls larger than about 3, and then here for the second excited state it breaks down even earlier but works well at it would work presumably well at large R, but out there it's very difficult to do the measurement on the lattice. And there's a good reason for this, because everything is exponential. So it's really the exponentials that you're fighting when you're making the string long. So it's not really plausible to just tell the people who are doing the lattice simulations to do it out here just because you can compute more easily. You should really think about a better way of doing the calculations and try to understand why this is actually breaking down. So this is what I'll discuss next.
Sorry, what are there's 3 different curves in each color?
Right now I'm only discussing the dotted one, and then as we'll go along we're looking at the other curves. Yeah. And so yeah, it doesn't really work well for excited states. Here I'm just showing very simple ones where you just have a single left moving or single right moving phonon. It looks even worse for the states where you have 2 quanta. So what we should do is we should really take more seriously the fact that we're on a circle. So here we compactified, but now we're somehow expanding the theory, imagining that the phonons here have momenta that are somehow 2 pi over R. And so what we should do is and you should ask how the momenta of these things are actually quantized. In a free theory, it's certainly true that they're quantized in 2 pi over R. If you have interactions, this is no longer true. So to see this, one way to see this is to look at the 2-particle wave function. So let's look at 2 of these guys. We have one of them at x1, another flavor here. And then let's say the guy with flavor I is a left mover, and we have one right mover with flavor J. And diagrammatically, what we're looking at is something like this. So we have the left mover with the flavor I, and then the right mover with the flavor J. And you can either really compute these kind of objects in perturbation theory and convince yourself that they have this structure, or just intuitively you can also kind of see what they should look like. If you look in the regime where sigma, so this guy we're picking up at sigma 1, so if sigma 1 is greater than sigma 2, then we're seeing it down here, so we're just seeing free particles before they scatter. This is if sigma 1 is greater than sigma 2. And on the other side, if you look at it after they scatter, you pick up the scattering phase shift. So this is when sigma 1 is less than sigma 2, we get e to the minus I p left sigma 1, e to the I p right sigma 2. This is also 2 here. And then you get e to the 2I delta p left, let's call it p left and p right. If sigma 2, well, let's write it the other way, sigma 1 is less than sigma 2. And so what we should impose is that this wave function is periodic if we're on the circle. And this now means that, so if we, so we want this to be periodic. In other words, the thing evaluated at sigma 1, sigma 2 should be the same as the thing evaluated at sigma 1 plus r sigma 2, and also the same as the thing evaluated at sigma 1, sigma 2 plus r. Let's look at the case where we impose the periodicity in sigma 1. Then the sigma 1 plus r, in this case sigma 1 is certainly bigger than sigma 2, so we get a relation. So from periodicity in sigma 1, what we get is e to the minus I. So I'm just evaluating this one at sigma 1 plus r and this one at sigma 1, because this is where the sigma 1 is less. So we have e to the minus I p left times r has to just be equal e to the 2I delta p left p right. This is for the two particles. And then if you take the log, so this is usually written in this way, p left times r plus 2 delta p left p right is 2 pi n left, and then you get the same equation for the right movers. And you see that in the limit where the theory is free, when delta goes to 0, you just recover the usual quantization condition that it's the momenta 2 pi n over r. But if it's in the interacting theory, it's actually modified. And you see that our phase shift, so the reason this is good for what we're trying to do is that this phase shift is p left times p right, so ls squared p left p right, which is in particular positive, which means that the solutions to these equations will actually be smaller. So the physical momenta of these quanta are actually less than the 2 pi over r that you would have naively expected. So this is one of the effects. What this is still ignoring is what we've done here is we're using, so this is, I should say, this is called the beta ansatz. So this generalizes if you have a bunch of quanta. So let me write it out again. So what we get is the quantization conditions that look like this. And then we're summing over all the flavors, all the particles with a given flavor, 2 delta that our guy scatters off. And this one has flavor I, let's say. Particle M is 2 pi n left, and then the same for the right movers. Okay, so what it ignores, what we're doing here is we're computing the S matrix at infinite volume. What it ignores are still the effects where particles, virtual particles, travel around the loop. So we still need to And here I just really mean the virtual particles. And well, before I do that, let me just say what the dashed line is. So the dashed line is just the solution for the beta ansatz, which in this case, because there's no right movers, it's just a left mover. It's just the momentum is just 2 pi over r for this guy. So it essentially looks like a free particle, really. And then there's the classical linear piece, the r, and here this is just 4 pi over r. So this is what the dashed lines are. Does that make sense? So then the question is, how do you take these things into account? And so this one, here I'm using that to the order we're interested in. The S matrix is factorizable, even for the left movers. I'm not assuming anything because they just don't scatter of any of other left movers. But for the states that I'll show in a second, I'm assuming still using that this is a factorizable S matrix, and in particular, I don't have to have no 2 to 4 processes, and so I only have to worry about the 2 particle states. So to take the finite size corrections into account, let's first think about the ground state, and the way it's done there is using the thermodynamic beta ansatz. Which I'm assuming you'll hear much more about from other people. I mean, no? Okay, so the basic idea is what we're trying to do. So the goal is, as I said, to compute the ground state of the theory when it's compactified on a circle with size r. What we can do is compute the partition function. So this is our circle, and this is length L. This is length r. The partition function, in the limit where we take L to infinity, we're taking the temperature to 0. So the partition function just goes to e to the minus L E0 of r in this picture. So we're just projecting onto the ground state. It's a relativistic field theory in 1 + 1 dimensions. So we can actually also think about it this way. This is L now. This is R. And we're now thinking of it as a theory at finite temperature with beta given by 1 over r and by r. And the L, taking L to infinity means we're taking the thermodynamic limit. So in this case, the partition function goes to e to the minus L times r times the free energy density. And so you see that you can get the ground state energy of the theory on a circle from the free energy density, assuming that you know that. And the trick now is that you can compute this. So naively, this doesn't help you, because if you could have evaluated this partition function exactly, you would have known this one. So here the idea is that because you're taking L to infinity, you're working in the thermodynamic limit, and you just use essentially statistical mechanics to evaluate the partition function over here using the beta ansatz we have over there. And I just really wanted to give you the basic idea. This is for the ground state. You can extend it to excited states using analytic continuation. I won't go through that. I also won't write down the explicit expression for the free energy, etc. I just want to give you the result. But this is the basic idea, and I'm happy to discuss it more if people want. But for now, I'll just state that there is such a thing, and it computes the finite size corrections that you need to the beta ansatz here. So this modifies the equations and gives you PL times R plus, and then the stuff we already had, 2 delta P left, P right, and this with flavor I, particle m, and maybe I shouldn't, well, we'll see if I keep writing all the indices. And then here we're summing, and then it looks like this for the system, where epsilon has obeys us an equation that essentially is the same as this one. So epsilon is p plus 1 over r. This one?
Yeah, the first term is the same as this, so they both do not complain. The second there is the integral with the log.
Oh, the integral with the log, yeah. Sorry. Hmm? It's the log of, let me just write it again, it's okay. This is also too small. Okay. It's better? You get this equation, and then you get a very similar equation for this guy. So this is the right one scatters of the left movers. And we have the 1 over r. Let me just make sure I'm writing the right thing, but yeah, here I'm writing, I guess, in the notes anyway, I wrote everything for the left movers, but it doesn't matter. So then this one is P and PRJ. And then if this is the left guy, this one's the right guy. And the same equations for the right movers, and then the energy of your state has the classical piece plus the energies of all your quanta. I won't write indices, plus, and then an integral d prime 2 pi log of 1 minus plus the same thing for the right movers. Okay, and you see, so in all these pieces are responsible for computing the finite size corrections. I mean, everything involving epsilon, and the interpretation is that, well, the naive interpretation is that these guys scatter off some thermal bath. And then this is the line that's shown here in solid. You get it from here. The nice thing about the strings is that if you look at these equations, you see, so these look like a mess naively because they're coupled integral equations. But what's nice about the string is that the scattering amplitude to leading order, at least, is just linear in P left. So this just factors out. So you can just make an ansatz where this is some constant times p, and then it will factor out everywhere. So this is all linear in p, and you get equations that you can solve analytically even for the string. And for the critical string, it just gives you the formula for the energies that you know. So if you compactify, so this is more of an aside, but if you compactify the critical string on a circle, you get a formula for the energies that looks like this. Too small again. All right. And maybe this looks familiar from the usual quantization of the string, but you can get it really from here if you plug in that delta of p left, p right is ls squared, p left, p right. All these equations will turn into a system of quadratic equations that you can easily solve, and you get this energy. So you can quantize the string that way in principle. The thing we have to do now is include the next order in our scattering amplitude. So we saw that there was a term proportional to d minus 26 s cubed, and so this is the thing that we have to include and that I'll show on the next slide. And I won't show you much of the details, but this is the data now for states which correspond to two of these quanta. So you have a left-moving phonon and a right-moving guy, and the different quantum numbers This one? Yes. Mm-hmm. Yeah. And one subtlety here, maybe one should say, is that this the calculations here were usually done with while ordering and zeta function regularization on a circle, and this does not actually respect the symmetries. So this actually breaks the symmetries. So you have to add a non-covariant counter term, which I mean, yeah. At leading order, it doesn't matter. Yeah. Yeah. Yes. I don't fully understand what the resummation is for these kind of states. Maybe Pedro knows. I'm not sure. For the states with a single left mover, it is just the resummation where you work with a propagator. So you take the full propagator for your virtual quanta to be the free guy plus the one where it scatters off the physical guy plus two insertions and so on. You can derive an effective. Sorry, this means this is my physical left or right mover, which I'm considering a state. So the states I'm considering were the ones I was showing here, where I have one phonon. I'm trying to compute the energy level for one phonon, one physical guy. And then this is my physical guy. I mean, I have it. I'm computing this guy in, so I have it on the left, and then I'm computing these propagators in the presence of these guys. Yes. Yes. Mm-hmm. Yeah, that's why I don't know. That's why I don't know what. Yeah, that's why I don't know what happens here I mean, otherwise I would also understand exactly what happens there. But in this case, I'm just saying in this case I know what happens, and it's these kind of diagrams. What you can do is then write an effective action for these guys, and just in that effective action do the one loop calculation that was